Welcome to This Explainer. Today, we're diving straight into a fascinating new archive study that challenges absolutely everything we thought we knew about how AI solves complex engineering problems. We constantly hear about artificial intelligence revolutionizing every industry under the sun. But what actually happens when the rubber meets the road? Or, more accurately, when the force vector meets the structural beam? So let's start with a really big question. If an AI can write flawless Python code and draft award-winning essays in seconds, what happens when it's faced with the diagrams and the rigorous, sequential math of a mechanical engineering statics test? It honestly seems like a task a supercomputer should just breeze through, right? Well, a brand new paper by researchers Tanner Culleton and Hung-Fu Chang put this exact question to the test. And the results are, well, they're pretty surprising. And this brings us to our core mystery. AI models right now are passing general, open educational benchmarks with flying colors. But when you put them up against specialized engineering statics, the branch of mechanics dealing with bodies at rest and the forces acting on them, they hit a massive brick wall. There is a complete disconnect going on here between general intelligence benchmarks and specialized diagram-heavy engineering. Here is how we're going to unpack this detective story today. First, testing AI on statics. Second, the diagram difficulty drop. Third, vision isn't the problem. Fourth, multi-step reasoning failures. And finally, rethinking AI workflows. Okay, Section 1. Testing AI on statics. The setup. Let's look at how researchers built a brilliant scientific trap to catch the AI's exact weaknesses. Now, they couldn't just feed normal textbooks to the AI because, let's face it, textbook formatting is incredibly messy. To test the AI fairly, they used a method called model distillation. This is a super important concept. Basically, by removing the noise of that unstructured text, they force the evaluation to focus entirely on the core problem-solving pipeline: input parsing, visual extraction, sequential calculation, and final answer generation. They essentially held the underlying physics constant so they could isolate exactly where the reasoning chain snaps. Their methodology was a really strict three-step process. Step 1, they extracted 25 text-only statics questions to use as a solid baseline. Then, Step 2, they constructed a new dataset by adding engineering diagrams into the mix. And finally, Step 3, they created another dataset by modifying the numerical values. They were systematically tweaking the inputs to see exactly where the AI would stumble. Moving on to Section 2, the diagram difficulty drop, the investigation. What actually went down when they unleashed the large language model on this carefully controlled dataset? The difference here is, honestly, night and day. The AI breezes through those text-only problems like a star student. It is highly effective and incredibly accurate. But the very second an engineering diagram and multiple mathematical steps are introduced, the accuracy completely plummets. It's a massive, highly noticeable decrease in performance. Now, here is the crucial point. It's not simply the mere presence of a diagram that's causing this crash. The researchers actually found that the accuracy drop isn't just about how complicated the picture is, it correlates directly with the amount of sequential math required to get to the end of the problem. Which brings us to Section 3. Vision isn't the problem, the twist. This is the plot twist of our explainer, the exact moment we realize our primary suspect is entirely innocent. Because when an AI fails a visual test, our very first instinct is to blame its eyes, right? But check out this quote directly from the study by Culleton and Chang. They state that the performance drop is not primarily caused by limitations in image recognition. Think about that for a second. Most developers would naturally assume the AI just can't read the image properly. But the researchers explicitly tested this, and they found that the vision-language alignment is actually perfectly fine. In fact, the AI perfectly reads and parses the free body diagram. It identifies the force vectors from the pixels with total accuracy. But here is the crazy part. It entirely forgets or scrambles those vectors 3 mathematical steps down the line. It literally cannot reliably carry the variables it just parsed through subsequent mathematical operations without making substitution errors. So, Section 4, multi-step reasoning failures. The breakdown. Let's try to understand what is actually going wrong inside the model's brain when these errors happen. The study pinpointed 2 very specific culprits for this performance drop. First, inconsistent multi-step reasoning across the solution stages. The model just severely struggles to maintain logical coherence throughout a long problem. And second, it suffers from a sort of variable amnesia. It has tremendous difficulty retaining and consistently applying the visual information it literally just extracted from the diagrams. This whole phenomenon is known as reasoning drift. Essentially, each additional math step you force the AI to take increases the probability of variable misalignment or logical inversion. And the truly dangerous part about this, the model's confidence remains incredibly high, even as its internal logic is completely falling apart step by step. That brings us to Section 5, Rethinking AI Workflows, the blueprint. Let's see how all this translates into actionable advice. How do developers and educators actually fix this structural failure? Well, this quote right here is an absolute game changer. The authors clearly state that prompt engineering alone cannot compensate for sequential reasoning drift. That means we can't just talk the AI into being better at math with clever prompts, or just telling it to think step by step. The failure is structural, not linguistic. We literally have to fundamentally change the architecture of how we use these tools. So here are the new ground rules for engineering AI workflows. First, treat all diagram outputs as drafts, requiring explicit step-by-step breakdowns before accepting anything. Second, automated verification. Since statics problems have deterministic mathematical constraints, you should use symbolic math libraries, like SymPy, to unit test those intermediate calculations. Third, use explicit prompts that force the AI to list extracted parameters and their coordinate systems before it tries to solve a single thing. Fourth, monitor consistency by logging variable substitutions to catch that reasoning drift early on. And finally, physically separate the vision parsing from the reasoning execution. Route the diagram extraction to a dedicated vision encoder, and then pass that structured output to a deterministic solver. For the educators and curriculum designers tuning into this explainer, your takeaways are pretty clear. You should absolutely use large language models because they're incredibly reliable for conceptual explanations and text-based problem decomposition. But they absolutely cannot be trusted to autonomously generate verified solutions for diagram-heavy, multi-step homework. Intermediate validation checkpoints aren't just helpful here, they are mandatory. I want to leave you with this provocative thought as we wrap up today. If an AI can see a complex structural problem perfectly, but literally cannot hold the thought long enough to mathematically solve it without drifting, what does that mean for the future of autonomous engineering? Until this cross-stage consistency is architecturally enforced, how much can we really trust autonomous systems to design our physical world? Thanks for joining me on this explainer, and keep questioning the technology that's building our future.